All right, welcome everybody, and welcome to Patricia Palacios, who will be the guest today. She's an assistant professor of philosophy of science at the University of Salzburg. She did her undergraduate studies in physics and philosophy at the University of Santiago in Chile, and then also an MA degree in philosophy, I believe, at the University of Santiago, before she moved to the LSE in London to do an MSc in, I suppose, logic and philosophy of science.
Philosophy of science, yes.
Yeah, in philosophy of science, and then a PhD at Ludwig Maximilian University in Munich. She is working in general philosophy of science as well as in philosophy of physics. In general philosophy of science, she looks at things like reduction, emergence, the role of idealization, and scientific explanations in general. In physics, she works in particular on statistical mechanics, phase transitions. She has a forthcoming special issue she's co-editing in Synthesis. Oh, sorry, I'm not up to date. It's published now on infinite idealizations, right? And it's with Synthesis and several publications, among them in philosophy of science and other specialist journals. Today she will be speaking about the problem of relaxation time in long-range interacting systems. Please, Patricia.
Thank you for the invitation and the very nice introduction, and for you for being here. So this is a joint project with Lupo Casetti from the physics department at the University of Florence. So I should give him credits from the beginning. Let's start. So when we look at this kind of astrophysical systems, like clusters of stars, this in particular is the globular cluster M13, then we see properties that remind us systems in equilibrium, right? There is a quasi-universal luminosity profile. There is some density associated to these systems. The number of stars remains constant in time, right? So the same happens when we look at different astrophysical systems like galaxies. This is a nice picture of the elliptical galaxy M87, very famous now because in the center of this galaxy they took that picture of the black hole not so many weeks ago. And the same, so there is quasi-universal luminosity profile. There's some quantities that remain constant in time, like density, number of stars, etc. So the natural question that arises is whether we can treat these systems as if they were thermodynamic systems in equilibrium, and moreover, whether we could use statistical mechanics to account for the approach to equilibrium in this kind of systems. Now, when we try to do that, the first problem that we see is that these systems are long-range interacting systems. As you know, in thermodynamics, we generally deal with short-range interacting systems where we neglect all long-range interactions. But here, since what puts together these systems is gravity, we cannot get rid of these long-range interacting forces, and we have to deal with them when we study the system. So the idea that these are long-range interacting system creates important disanalogy with the systems that we generally study in thermodynamics. One of the disanalogies, which is very problematic, is the relaxation, or concerns the relaxation time. So let us go back to relaxation time in short-range interacting systems, and let's take the most simple example that we can possibly take in thermodynamics or in statistical mechanics, that is the gas in the container. So in short-range interacting systems, if we imagine that we have the gas in some part of the container separated from the rest of the container from a membrane, and we imagine that we take out that membrane, then we will observe that the gas, of course, reaches equilibrium as here, right? Now, the particles in these systems will travel at a typical velocity that we call v, and there will be a typical distance among the particles that we call L. The evolution of these particles will be described by the Boltzmann equation, and there is an important feature that independently on the initial conditions, the system will eventually reach equilibrium that will be well described by the Maxwell distribution. The relaxation time in these short-range interacting systems is going to be proportional to that typical distance over the typical velocity, and it will be completely independent on the number of particles. That means that as long as we are not considering systems that are too small, it doesn't matter if we consider a small system or a very big system, they will all equilibrate at the same rate. Yeah? This is partially because we are neglecting these long-range interacting forces. Now, with long-range interacting system, we have a situation that looks like that, but there is an important difference with respect to the relaxation time. So in this case, as they are long-range interacting system, the interaction potential will decay slowly with the distance, right? There will be a collisional evolution that will not be governed by the Boltzmann equation, but by the Fokker-Planck-Landau equation. But there will be an H theorem available, which means that eventually and independently on the initial conditions, the system will achieve this equilibrium that is, again, well described by the Maxwell equilibrium, as in the case of short-range interacting systems. Now, the relaxation time here, which is the time that it will take for the system to reach to that Maxwellian equilibrium, is going to be proportional to the number of particles, in contrast to the case of short-range interacting system. In particular, it will be proportional to the number of particles over some logarithm of the number of particles times this crossing time, that is the radius of the astrophysical system that we are considering over the typical velocity, right? As we will see briefly, this is very problematic. But in principle, if we neglect this analogy with respect to the relaxation time, we have a situation here that looks very similar to the case of short-range interacting systems. And as Craig Callender said, if we are neglecting the problem of the relaxation time, then it seems that in the case of long-range interacting system, we have everything what we need. So he says, what I want to point out is that for the Fokker-Planck equation, one of the most successful kinetic equations in astrophysics, one can get everything one wants. In particular, for many broad classes of collision terms, one can prove an H theorem. One can show that this H function is related to the Boltzmann entropy in the same way Boltzmann does for the dilute gases. Yeah. But here we are neglecting the problem of the relaxation time, which is not a minor problem. So let's go back to that. If we estimate the relaxation time that is proportional to the number of particles for galaxies that have approximately n equal to 10 to the 11, and in the case of the AIM 87, 10 to the 12, then we can estimate that the relaxation time, that means the time that it will take for the stars to get to that state of equilibrium in which we observe them, is 8 orders of magnitude larger than the age of the universe. Which is puzzling, right? So this leads to what was called for a long time the fundamental paradox of stellar dynamics, that on the one hand, the distribution of velocities, for example, in elliptical galaxies, is close to Maxwellian distribution, not exactly Maxwellian distribution, but close to Maxwellian distribution. On the other hand, the relaxation time, that is the time that it would take the stars to get to that equilibrium state, is much larger than the age of the galaxy, much larger than the age of the universe. So how can that be? How can this distribution be achieved if the relaxation time is much longer than the age of the galaxy? Yeah. So with respect to this question, one can have different attitudes. One attitude is to think that the whole idea of applying thermodynamics to astrophysical system and try to explain equilibrium in terms of statistical mechanics doesn't make so much sense. We should restrict thermodynamics and statistical mechanics to the systems that we originally wanted to explain with thermodynamics and statistical mechanics. And that's the attitude of Rawlinson. So he says thermodynamics is essentially a human science. It started with steam engines and went on to describe many physical and chemical systems whose size is of the order of a meter. Its laws are not truly a theory, but a highly condensed and abstract summary of our experience of how such systems behave. we have therefore no right to expect them to apply to other quite different systems, whether extremely large or extremely small. They clearly are inapplicable to the solar systems or to galaxies. So that's one of the possible attitudes that we can have when we see these analogies between the systems usually explained in thermodynamics and this kind of system. Another attitude, which is the one that I want to support, endorse today, is don't give up to the project of using statistical mechanics to explain the equilibrium states in which we observed astrophysical systems, but try to give a redefinition of equilibrium that suits better with these systems, and also try to suggest a different mechanism that brought the stars to the apparent equilibrium in which we observe them. So that is what I will endorse today. The idea that there might be a different mechanism that can be explained by statistical mechanics that brought the stars to the state in which we observe them nowadays was firstly suggested by Lyndon Bell in 1967. So he basically said that what gave the galaxies the distribution of stars in which we observe them wasn't this collision evolution, but a different process that had to do with large-scale fluctuations in the mean gravitational field during the collapse of the galaxy. So this means that there is a different evolution equation associated to this process, that is the collisionless Boltzmann equation or the Blasov equation, in which the collision term is neglected. Yeah? Here, phi is the self-consistent potential. So the nice thing is that if we consider this dynamic equation, then we can redefine the relaxation time in a way that is independent on the number of particles. So the relaxation time, due to violent relaxation, will be only dependent on the potential and the energy, and it will be completely independent on the number of particles. Moreover, one can estimate that this time will be very short in comparison to the lifetime of the stars. So it seems that this is a good way to go to solve the problem of the relaxation time. So there is just a different definition of relaxation time because there is a different mechanism that brought the stars to the state in which we observe them. Now, there is another problem here, namely that this Blasov equation admits an infinite number of stationary solutions. And to determine to which of these solutions the system will evolve is not very easy. Actually, it's very, very hard. So this brings us to a dilemma. On the one hand, if we maximize the entropy by using the collision dynamics that is analogous to the Boltzmann equation, then the distribution will be achieved in a time that is much larger than the age of the galaxy. So we will have a relaxation time that is much larger than the age of the universe. On the other hand, if we use the collisionless dynamics or the Blasov equation, then there are many different equilibrium configurations for a collisionless system. It is not clear to which of these configurations the system will evolve. Right? So here, there are again two different attitudes in the physics literature. One attitude was try to redefine entropy so that these quasi-stationary states in which we observe galaxies can be redefined as maximizing the entropy. In this way, we could get rid of the dynamics and we could try to give an account of equilibrium that doesn't oblige us to consider initial conditions of the system. The other option is to treat the system, this quasi-stable equilibrium state in which we observe the galaxies, as if they were out of equilibrium, evolving slowly to an equilibrium that is well defined by Boltzmann equilibrium. This is the more hard way to go, because this would oblige us to consider the dynamics. In this case, the quasi-stable state would not maximize the entropy, so we would have to take into account initial conditions. in order to determine to which of these states the system evolved. So unfortunately, proposals in this direction don't seem to work. So the only path available is the second one, that is the more hard way of solving this problem. So let me now tell you why this proposal of try to redefine entropy don't work. So one proposal that tries to redefine the entropy was done by Salis. So he suggests to replace Boltzmann entropy by this other expression that leads to Q distributions of this form. The problem with this proposal is that it only applies to so-called stellar prototypes and don't apply generally. So most of the states that can actually be defined by Salis entropy just don't correspond to the states in which stars actually are. And something similar happened to this Lindenbell approach. He also suggests to redefine entropy based on this violent relaxation. He assumes ergodicity. He assumes that the system mixes well, and define entropy in this form. And here these quasi-stable states are all, again, as in the case of short-range interacting systems, obtained by maximizing the entropy at fixed mass energy, but with considering Casimir invariance. By redefining the entropy in this way, he obtained what he wanted, namely that this distribution function will depend only on the energy and it will be monotonically decreasing, so it will also maximize the entropy in the end. But now the problem, again, is very similar to the problem of Salis entropy, and it's that this Lindenbell entropy don't describe well most of the stationary states in which we observed the stars. Why is it that? It's because he assumes ergodicity, and ergodicity is a very strong condition to assume in the case of self-gravitating systems. So it seems that the only possible way to go is this second alternative, and we have to treat the systems as if they were out of equilibrium, so, approaching slowly this equilibrium that will be well described by Boltzmann. So this is the strategy that we take as well, and for us equilibrium will be something like what Feynman describes as equilibrium. So in this case, equilibrium will be the state when all the fast things have happened, but the slow things have not. Now, we try to motivate this new definition of equilibrium with an analogy in short-range interacting systems, in particular with the phenomenon of ergodicity-breaking in short-range interacting systems. So, as you know, ergodicity plays an important role not only in Boltzmann statistical mechanics, but also in Gibbsian statistical mechanics when we want to relate time average with phase average. In order to show that they are equivalent, we need to assume that the system is ergodic. And ergodicity, as you know, is the assumption that the system will go through all or almost all points of the phase space for a very long time or for an infinite time, right? So this assumption of ergodicity in order to define equilibrium has been very controversial. One of the reasons is that it's very hard to test that the systems are actually ergodic. But most of physicists accept that at least many systems can be plausibly be considered as approximately ergodic, right? Now, there are some systems in which ergodicity is not even approximately true, but is manifestly false. And those are the systems in which ergodicity is broken, for example, in the case of magnetization flips. So if we use the Ising model to describe the behavior of a ferromagnet at a very low temperature, we will see that the system can flip from these two ground states that are the positive magnetization and the negative magnetization. Now the lifetime, which means the time that the system will spend in each of those ground states, will be dependent on the number of particles, as here. Which means if the number of particles is large, then the system will be for a long time in one of those metastable states. If the number of particles is shorter, then the system will flip more quickly. Now, since this lifetime is proportional to the number of particles, if we take the thermodynamic limit, which implies assuming that the number of particles go to infinity, then the system will get stuck in one of these metastable states, which means that it will get stuck in one of the in some region of the phase space. And this is ergodicity-breaking, because the system, not even in an infinite time, will visit all the regions of the phase space. An interesting aspect of this thermodynamic limit is that if we consider this system, we observe that the thermodynamic limit and the infinite time limit don't commute. If we take the infinite time limit before the thermodynamic limit, then we will get the Gibbsian statistical equilibrium and also Boltzmann statistical equilibrium. But if we take the thermodynamic limit before the infinite time limit, we will get one of the system will get stuck in one of these metastable states.
So that's for the ergodicity breaking.
That's for the ergodicity breaking. That's for the case of magnetization flips, which is an interesting aspect because this is one of the cases in which infinite limits don't commute. So now the moral here is that if one wants to account for a magnetized system, a system that is either in this ground state or in the other ground state, then one cannot take the infinite time limit before taking the thermodynamic limit. Now, we realized that there was an interesting analogy with this case and the case of long-range interacting system. In the case of long-range interacting system, one also can use these two infinite limits, and the infinite limits don't commute. If one takes the infinite time limit before the thermodynamic limit, one will get the Boltzmannian statistical equilibrium, because we will be considering an infinite time limit, so the time scale will be larger than the relaxation time. But if we take the thermodynamic limit before the infinite time limit, then we will obtain these quasi-stable states that are different from the Boltzmannian distribution. Now, since in the case of long-range interacting system, we're interested in giving an account of these quasi-stable states, which we think are the states that describe the quasi-equilibrium in which we observe this astrophysical system, then the moral is that we cannot take the infinite time limit before taking the thermodynamic limit. Or respectively, we have to take the thermodynamic limit before taking the infinite time limit in order to obtain stationary solutions. But this analogy is more interesting because it doesn't concern only this non-commutability of the limit, but different properties that magnetization flip and long-range interacting systems have in common. So in both cases, the system will get stuck in a limited region of the phase space, in a metastable state. So in both cases, we have ergodicity breaking. In both cases, there is a dependence between the initial and the finite state, which means in both cases, there seems to be a dependence on the initial conditions. In both cases, the relevant time scale depends on the size of the system. In the case of the magnetization flip, it is the lifetime that depends on the size of the system. Not the relaxation time to one of these metastable states, but the lifetime in the metastable state. And in both cases, the limits don't commute. So one can make this analogy more precise with this schema. So in the case of short-range interacting systems like magnetization flips, one starts from initial condition, and after a relaxation time that is independent on the number of particles, one will achieve a metastable equilibrium, right? That can be one of the two ground states. Now, after a long time that is much larger than the lifetime, that is proportional to the number of particles, we will obtain Boltzmannian equilibrium. In the case of long-range interacting system, one starts from initial conditions, and then after a short time, compared to the life of the universe, that correspond to violent relaxation and is independent on the number of particles, we will arrive at Blasov equilibrium, which is also a quasi-stable state. And after a larger time, that is given by this collisional relaxation, that is proportional to the number of particles, we will obtain Boltzmann equilibrium. So then, based on this analogy, we suggest that the qualitative definition of equilibrium in the case of short-range interacting system that implies symmetry breaking can help us to give a qualitative definition of equilibrium in the case of long-range interacting systems. Moreover, we think that this analogy motivates the whole enterprise of trying to use statistical mechanics in the case of long-range interacting systems, because it is basically the same process that we have to do here, what will allow us to understand equilibrium in this other case. So let me now explain how can we redefine equilibrium for ergodicity-breaking phenomena. So here there is a nice connection to the work that a colleague of mine has been doing, Charlotte Berndt and Roman Frick. So they wrote a paper in 2017 where they encouraged to mind the gap between Gibbsian equilibrium and Boltzmannian equilibrium. So for them, Gibbsian equilibrium is always associated with stationary probability distribution, right? Whereas in Boltzmann equilibrium, we take into account the time that system spends in the regions of the phase space. So according to Gibbsian, they actually study the case of magnetization flips to illustrate their point. And according to them, if we define Gibbs equilibrium for the case of magnetization flip, we will show that the magnetization in this, or the equilibrium state for the magnetization flip is always 0, because we will take the average of the two more likely states, right? Now, in the Boltzmannian equilibrium, since we are taking into account where the system has spent most of the time, we will not average between these two more likely states, but we will have a dual equilibrium, which actually give us an account of where in which regions the system has spent most of the time. In this case, we will have a dual equilibrium between the two ground states of the system. Now, we think that this definition doesn't apply literally to the case of long-range interacting system in particular, because these quasi-stable states don't maximize the entropy. But we think that it is a Boltzmann understanding of equilibrium that takes into account the time that the system spends in the regions of the phase space, which give us, at least intuitively, an idea that is closer to the definition of equilibrium that we have to give for long-range interacting systems. So, in the case of magnetic flips, we might be interested not only in giving a definition of equilibrium and say where the system will spend most of the time, but we might be interested in predicting exactly to which of these metastable states the system will evolve given some initial conditions. And we might be interested also in estimating the precise lifetime in which the system will be in some particular metastable state. In the case of magnetization flip, one can do that precisely. There is a very well-defined expression for the lifetime that will allow us to estimate for how long the system will be in the metastable state. And there is a very well understood dynamics in this system, which tells us exactly which initial condition we need to consider in order to predict to which of these metastable states the system will evolve. And in the case of the magnetic flip, these initial conditions are very simple. If we start with an initial state that have more spins down than spins up, then the system will evolve to the negative magnetization. If we start with a state in which there are more spins up than spins down, then the system will evolve to positive magnetization. And with a very simple dynamics, we can predict after how long the system will reach metastable state, for how long the system will stay in that metastable state, and basically we have all the information that we need, even if there is some dependence on the initial conditions. Now, we believe that something like this is precisely what we would need in the case of long-range interacting system. One is also interested in predicting for how long the system will stay in a metastable state. And one is interested in predicting how much time did it take for the system to reach that equilibrium state in which we observe them. Now the problem is that after using this qualitative understanding of equilibrium and extrapolating it to the case of long-range interacting system, one sees more clearly all the complications that long-range interacting systems imply. In particular, the dynamics here is not as simple as in the case of magnetic flips. It's very complicated. Chavani tried to develop a dynamical theory of violent relaxation of this form, where this D is the diffusion coefficient. So solving this equation is not very simple. One can assume, again qualitatively, that since this diffusion coefficient depends on the fluctuations, and fluctuations in the end were responsible for this equilibrium in the astrophysical system, one can assume that when these fluctuations, when the diffusion coefficient vanishes, that means that fluctuations have stopped being important, being influential for the behavior, and get the system stuck in some particular metastable state. But the problem is that, again, predicting exactly to which quasi-stable state the system will evolve, in which quasi-stable state the system will get stuck, depends on considering the dynamic equation, and depends on the initial conditions, which are not very easy to estimate in this case. So an important difference with respect to the magnetization flip case is that the quasi-stable solutions don't depend on the energy alone, and thus does not maximize an H function. Moreover, the Blasov equation can have very complicated non-ergodic dynamics. In some cases, the system may not even relax to a stationary state of the Blasov equation, but might develop everlasting oscillations, which make the estimation of the evolution to this quasi-stable state much more complicated. So, but at least this qualitative understanding of equilibrium give us an idea of the kind of questions that physicists need to answer. And this is exactly the state of the art. So these are all open questions. They don't know yet how much does the final state, this quasi-stable state, depend on the initial conditions, or which are the initial conditions that matter. Of course, one sees some universal behavior in these astrophysical systems. There are particular kinds of galaxies, so there cannot be an entire dependency on the initial conditions. There might be some initial conditions that matter and some others that don't, because the systems seem to be robust under certain initial conditions, but they don't know which initial conditions precisely matter for the behavior and which don't. They also don't know for how long the system is going to be stuck in a particular state, which would be an interesting prediction, because one could know for how long the system will remain in that apparent equilibrium in which we observe them. So there have been some work, as you see, very recent work that has been done in this direction, but this is all work in progress, and there are still no concrete results that solve this, that answer these questions. So one of the projects have consisted in restricting to a subclass of well-behaved systems that can be well described by these new definitions of entropy that maximize entropy. like Sally's entropy or Lindenbell entropy. The other strategy has been trying to build analogies with similar systems like what we are doing. For example, Rapisada and Pluchino have proposed analogies with glassy dynamics. There is also a prospect of building this analogy with magnetic flips further and try to give more quantitative predictions. Another strategy has been based on computer simulations, this Hamiltonian mean field model, for example, where they have tried to estimate a lifetime that they think would be approximately applicable to some stellar systems. And the other strategy, Pachter and Levin, for example, have developed a solution that starts by considering Lindenbell well-defined solutions and then add dynamic effects so one idealizes the situation and make it a little bit more realistic. Lapo himself, my co-author, is trying to develop now a line where he tried to apply renormalization group methods to try to visualize which are the initial conditions that matter. But in general, these quasi-stable states is mostly non-universal, as it depends on the detailed structure of the initial conditions and on the efficiency of mixing, which make the task more complicated. So this is the state of the art. Now what can we conclude from what I have said? So the understanding of equilibrium in terms of stationary probability distributions doesn't seem to fit well with the case of long-range interacting system. One can say, with respect to idealizations, that the infinite time limit is not an appropriate idealization, because if we take infinite time limit, then we will obtain this Boltzmann equilibrium, but that's not the equilibrium that describes the quasi-stable states in which we observed astrophysical systems. A comparison with ergodicity-breaking phase transition gives us a qualitative understanding of equilibrium for the case of long-range interacting systems in terms of metastable equilibria. But, well, as in the case of phase transition in long-range interacting systems, one could account for metastable equilibria by defining the dynamics for finite time scale, but in contrast to phase transition, the dynamics in this case, in the case of long-range interacting system, is much more complicated, and one doesn't know really which are the initial conditions that will be relevant for the evolution to particular quasi-stable states. So much more work needs to be done in this direction in order to understand these quasi-stationary states and their dependency on initial conditions. So thank you.
Thank you very much. Who would like to go first? Maybe I can get the ball rolling here.
Yes.
What exactly are the systems we're trying to model here? Say long-range interacting all the time. What's the target? Can you say a little bit more about that? I mean, what assumptions do you make?
Yeah. I think the title might be a little bit confusing, because we said that we want to give a definition of equilibrium for long-range interacting systems, but in the end, all our examples are self-gravitating systems.
Right,
We're gravity, so we are not thinking about Coulomb force yet.
Right.
But
okay.
so for now we are considering self-gravitating system, but the idea is try to extrapolate it to.
So it's self-gravitating systems, and what? I mean, more specifically, what are these systems? What do you assume about the gravity that they're subject to? Are there any any theoretical backgrounds, or is it just excuse me something, or is it more some observational data that you try to track to get right? I mean, what is a self-gravitating system?
Yeah, so actually it's even a subclass of self-gravitating systems. It's actually a self-gravitating system, well, in which basically gravity does the main work of defining some particular shape and all the other properties that allow us to describe the system macroscopically, if you want, like luminosity in terms of luminosity profile or density and so on. But then the subclass of systems that we are interested in are these systems that are big enough so that you cannot use the collision equation. Because in clusters of stars, that was the first image that I showed, and those systems are small enough so with the collision, so that you can explain the evolution to the system just by using the collision equation. But these are other systems like galaxies, more than 10 to the 10 or more, in which the implication or the relaxation time will be much bigger than the age of the galaxy, so it needs to be another mechanism that explains that. Okay. So I can say that we are focusing on galaxies and those kind of subclass of gravitating systems.
This is what you have in mind. And what you know about those systems derives from a combination of general relativity and maybe statistical methods, maybe some ideas about particle physics or something, or at least some sort of general idea about astrophysics, about relating luminosity to other properties of the system, and then presumably some observations of that kind of system to see these relations confirmed.
Yes.
That's the kind of target you have in mind.
Yes.
Okay.
Yes.
Good. And for these combined reasons, you then have reason to believe that they are, there is this paradox in operative, I suppose, in those sort of systems. Good.
Yes.
I should.
Yes. No. Sorry, I didn't. Yeah. So the title is much more general than what we do.
Trying to be a little bit clearer, exactly.
Yeah.
But thank you. That's very helpful.
Concerning this dilemma, so you were talking about as one horn of the dilemma, you then have to bite into many different equilibrium states, right? So one of them would be like the Maxwellian distribution, I guess, right? But what would the others be like? Just like all kind of possible different equilibria, or just a finite amount of other equilibria? Or?
Yeah, it can be infinitely many things, and that's one of the problems, right? So in one case, in one horn of the dilemma, you have a well-defined entropy that coincides with Maxwellian distribution and that is independent on the initial condition. So you have a very clear understanding of equilibrium. In the other case, you have quasi-stationary states that don't maximize the entropy. So you can basically have infinitely many possibilities of distribution of velocities and so on.
Okay. And there's no sense of like local equilibrium or so? I don't know, if you stay in a certain regime that you might still explain why you go to this equilibrium rather than to others? Or maybe this question doesn't make sense because I don't know. But yeah, maybe, I don't know.
Yeah, that's one of the open questions.
Yeah, okay, I see.
I'm sorry, very slow. I'm trying to sort of reconstruct
please.
your argument step by step.
Yeah.
So I think I have a better idea now of the class of systems you're looking at. Now, when we look at those systems, we find velocity distributions, I think it was, that were sort of close to Maxwellian equilibrium, yet, if you would treat this with the usual sort of thermodynamic methods, you to that kind of equilibrium clearly must exceed, at least as usually defined, the age of those systems. That they cannot really have reached that equilibrium in the way we would normally have thought of a thermodynamic system.
Yes.
And that leads you to either to redefine the relaxation time or the mechanism by which they relax, or to reject the entire project of understanding those things with thermodynamic means altogether. Right? That was at the beginning, and then there was some author cited by Calendar who voted for the second option. But can you say a little bit more why you reject that option? Would you try to go the other way?
Yeah, well, because I think the situation that we have here is not so different from what we have in short-range interacting systems. And using statistical mechanics to define the short-range interacting system in which there is ergodicity-breaking has been very useful for making predictions. So there is at least some hope. Even if it's much more complicated, at least there is some hope that the same could be done in this other context. So that's basically the point that we are trying to make.
So if I understand you correctly, the main reason for dismissing that strategy or that reaction is because you think that there is a potentially fruitful way of dealing with it. So it's kind of unnecessary to throw all of this out. I mean, could you do something like that? No?
Yes.
Okay.
Yes.
Florence?
Yes. I have a very broad question.
Yes.
So if I understand you, the strategy to deal with these cases is to give new definitions to entropy and equilibrium, right? So just a very general question is, a very general worry about this is that, if you redefine the terms, right, you may just be changing the question. So I view some way to describe the facts we want to explain in a neutral way, and then we can show that if we think about these new concepts, which we have attached to the same names, but now they have new concepts, we can explain some facts that we can describe in a neutral language. There's something we can all agree on. The question is what is to be explained. Well, immediately, if you don't understand what I'm asking, maybe I can try to respond.
Yeah, can you reform it? Sorry.
Basic fact about definition is that they are non-creative, right? If you just can derive certain results, you cannot extend the results you can derive by introducing a definition. In the same language as before. If you can derive a result, whether you introduce a definition or not doesn't change. You can do it still. Maybe what you can do is that if you introduce a definition, right, it will draw your attention to certain facts you hadn't thought before and certain line, but you can derive something, right, which you can state without, doesn't depend on the definition. So the question is, because if I had a paradox at the beginning, and I cannot see how to resolve that, if I just take the words in the paradox, and I change the meaning, and now I can explain that, I haven't really solved the whole paradox. So my question was, if I now concentrate on this new notion, I have a new notion of equilibrium and I have a new notion of entropy. And I think in terms of that, and I need to have something to say about it. How does it explain some of the old facts? How does it solve the paradox and so
on? So I talk about a paradox and I talk about a dilemma.
Yeah,
I think with this proposal one solves the paradox but doesn't solve the dilemma. So the paradox was that one seemed to observe, so the system seemed to be in equilibrium, galaxies for example. But if one uses the collision evolution, then one can estimate that the time that it would have taken for the system to achieve that equilibrium would have been much larger than the age of the stars and the universe, right? So I think the way of solving that paradox, like the question then is how can it be, right? The way of solving that paradox is just assuming that there is a different mechanism that brought the systems to the quasi-equilibrium in which we observe them, right? And that's what we consider violent relaxation in this Blasov equation. So I think that's the solution of the paradox. We are not redefining terms here, we are just explaining. So the question is not, it's absolutely, yeah. So the question, it's absolutely answered by saying, well, there's another mechanism. And the thing is that if you observe carefully, then you will not see that the systems correspond to equilibrium in the Boltzmannian sense. But there's still an explanation of that equilibrium in which you observe the system. Call it quasi-equilibrium state because it will eventually move away. So in a way, it doesn't correspond to the equilibrium that we have in statistical mechanics. But it answered the original question, that is, how can it be? So the original question didn't have to do with the definition of equilibrium as defined by Boltzmann. It had to do with the constancy of some quantities in time that you would consider equilibrium in the explanation of that, right? So I think that's answered with this strategy. The dilemma is not, we are inside of the dilemma. So the dilemma was, well, on the one hand, if you maximize the entropy and you get rid of the initial conditions, then you estimate that the relaxation time is much larger than the age of the universe. And the second part of the dilemma was, well, if you use Blasov equation, then you have infinitely many solutions. In that case, we say, well, yeah, you can still give a definition of equilibrium, but you will keep that problem because one of the main issues now, even if you understand equilibrium differently, is that you don't know to what extent this behavior depends on which initial conditions.
No, but it was asking.
So the dilemma is not solved. The paradox. The paradox is solved. Actually, that no one call it the paradox of stellar dynamics anymore. That was called for many years the paradox of stellar dynamics, but not anymore, because many people believe that Lindenbell gave a nice solution to it.
Thank you. So I don't know a lot of that, so just want to understand a bit more what's going on. So what I understand, there is this qualitative comparison between long-range interacting system on the one hand and ergodicity-breaking phase transitions on the other hand. And just could you say a bit more on the long-range interaction side? We also have a failure of ergodicity there, or not really? Because I was thinking, is the situation that we have, the idea that we have two tokens of a more general situation, a more universal situation, namely a failure of ergodicity, and so there would be some kind of motivation for thinking that there is not something specific there because it's a failure of ergodicity that we have in other places in physics. Or could you say a bit more? Is it roughly right?
Yeah. You do. It depends on how you take the limits, whether you have ergodicity breaking or not. If you don't take the thermodynamic limit, you will not, because the system will be stuck in a metastable state for a long time, but eventually will move towards Boltzmannian equilibrium, and you might assume that the system is ergodic to some approximation. But if you take the thermodynamic limit to obtain these stationary solutions, then you will have ergodicity breaking because the system will be stuck there forever, exactly like in the case of magnetization flips in short-range interacting systems. Now, we are not focusing on this ergodicity breaking so much. We are focusing on the analogy of these relevant time scales. So now in short-range interacting system, in many you don't have strict ergodicity, but there are some short-range interacting system in which the ergodicity is broken. So the system gets frozen in one region of the phase space. Now, if you don't take the thermodynamic limit, the time in which the system will stay in one of the metastable states is going to be proportional to the number of particles. And that's very similar to what happens in long-range interacting systems, where the time that it will take for the system to achieve equilibrium is also dependent on the number of particles. So those are the kind of analogies that motivate this, or like analogical properties that motivate the analogy between these two cases. Is that clear enough?
It's where in my head, still trying to understand.
Yeah.
Okay, so I'm trying to understand the mechanism, the specific mechanism. So if I understand it correctly, the Lindenbell mechanism of violent relaxation, you accept that as the basic mechanism of relaxation, those elliptical galaxies. But how does that, can you go back to the slide maybe where that's introduced? I'm sorry, I warned you that I'm slow, so.
No, that's fine, that's fine. Yeah, sometimes one
But
thinks
we're
that.
getting there, I think.
No, okay. There.
This.
Yeah.
Okay, yes. Large scale fluctuations. So we have the gravitational field in a galaxy. When the galaxy collapses, how so?
The collapse, it's just talking about the formation.
Formation,
Yeah.
its form.
Yeah.
I mean, collapse to me sounds like it's forming a black hole. It's
No. That's another use of the term by astrophysicists. Yeah.
Okay.
Yeah.
The
Just
formation
the
of the
formation.
galaxy.
Yeah.
Okay.
We are not talking about black holes here. That's why,
Yeah.
as I said before, we are restricting this
No,
study.
it's fine. Okay. And these large-scale fluctuations are because the parts of the galaxy are like wobbling around, and this creates, quite significant fluctuations in the mean gravitational field, of course.
Yes.
And it's that these wobbles which force the stars rather quickly into that velocity distribution one would expect of an equilibrium state.
Yes, it's very close to a second order phase transition, what is happening here. So you have the mean field and you have fluctuations dominating the behavior that also explain some kind of singularity power laws. So here there are no power laws that describe the behavior, but qualitatively it's the same idea. So are these fluctuations that explain this sudden equilibrium in these systems.
And initially we didn't get the relaxation to happen so quickly because we didn't take into account these fluctuations.
Yes.
Okay.
Exactly.
Okay.
Yes.
And then, sorry if I go wrong, please, other people should ask as well. I feel like I'm
Please ask me everything. This is actually a controversial project, so I am happy to receive questions and criticisms.
Good. Now, okay, so I think I understand the project so far, but now the big question is really for me, okay, so here we have these elliptical dynamics with some mechanism of approaching equilibrium in the distribution of the velocities of the stars. But based on what is it? Maybe that's similar to Baptiste's questions. Based on what exactly is it? Are we hoping to learn something from these short-range symmetry-breaking systems? So there are some analogies between those and here. But what makes us so confident about these analogies? What's the justification for really thinking that we learn something about elliptical galaxies when we look at, sort of Ising models?
Yeah, to the extent. No, it's fine. That's the big question. I
That
think.
is the big
So
question.
That's
Yes.
the point that we want to make.
Exactly. Now I understand this is the point you want to make. So
how can we be sure that the analogy?
maybe asking how you can be sure is asking for a little bit too much.
Yeah.
But you're confident that we can learn something from the Ising model that's applicable to the elliptical galaxies.
Yes. Why?
What's the basis of your confidence?
Yeah, this analogy that I draw here, that they coincide in many, or they are analogous in many properties.
Mm-hmm.
So in both cases the system gets stuck in a region for a second. I will not call it proper ergodicity breaking because it might get stuck for a long time and then move on. But it gets stuck at least for a certain time in some region of the phase space. There is dependency on the initial conditions for these metastable states. The limits don't commute. And in the fact that the relevant time scale depends on the number of particles. We are based just on these similarities between the two systems, just to say, to make it plausible that in the same way in which we understand equilibrium for the case of short-range interactive systems that imply ergodicity breaking, will help us to give a qualitative equilibrium for the case of long-range interactive system. And moreover, because that's not the only thing that we want to do, moreover, once we have that definition of equilibrium, then we can understand, based on this analogy, which are the following steps that we need to do in this other case to understand better some properties of this equilibrium, or some, for example, for how long the system will stay in some of these states.
There are also some disanalogies. For instance, like in the Ising models, you have two metastable states, right? And if I understood it correctly from the Vlasov equation, there's many.
Yeah.
Infinitely many, I forgot, but a large number.
Yeah.
So that might mean that's going to be a very different problem.
Yeah, that's why you should not understand it exactly in the same way, but that can help you to start, first of all, motivating the project. Because the situations are similar, and in one case, using statistical mechanics have been very helpful to make predictions. So you can assume that if this situation is somehow analogous to the previous one, then you can motivate the use of statistical mechanics as well. But it's true, there are some differences that need to be considered, and that's also what we were pointing out. So one of the differences is that the dynamics is much more complicated, and that's not a trivial difference. So that in the case of magnetic flips, you need a very simple initial condition to know to which state the system will evolve, and that's what made the whole application of statistical mechanics so interesting, that you can do that. There's no promise that you will be able to do the same in the case of long-range interactive systems because the dynamics is so complicated. But at least we believe that if you have some qualitative understanding of equilibrium that is somehow analogous to another situation that you have in short range, then you have more motivation to apply statistical mechanics. There's no guarantee.
No, of course.
But it's
I'm not asking for a guarantee.
At least there is more motivation. But what physicists are doing, including Lupo, Michael Alpha now, is try to study magnetization flips in which the system don't go from one ground state to the other, but get stuck in some metastable states in between that don't maximize the entropy. And there is some observations on that, and that case is much more realistic or much more closer to the long-range interacting or the
So,
elliptical galaxy
okay.
that we are studying, right? So, but one starts with that very rough analogy, and then one try to make the situation or get closer
I see.
to a situation that is.
So I can see that this can be a useful heuristic. So it may be initial motivation to pursue a research project, but I cannot help to find it somewhat vague. And,
Yeah. It's not. Yeah, it's not a perfect analogy. It might be that the whole that they don't obtain any qualitative result in the end. And
maybe one more
Please, please.
follow up. When astrophysicists observe elliptical galaxies, do they find different metastable states? Or, I mean, that could be a source of input that gives us a bit of an indication of what's going on. Or is it always the same
yeah,
Maxwellian distribution that we find?
that was also some bad use of language that I did at the beginning, because they just assumed that the distribution was closer to the Maxwellian, but that wasn't a very precise estimation either. Now people that are within this project are thinking that the distribution is not close enough to Maxwellian, and that's why we in particular need to understand the evolution to this quasi-stable state. Because just by assuming that it's close to Maxwellian doesn't give us enough account of the system in which these astrophysical systems are in.
Okay. Well,
So I think you had the best chance to say something useful, but I have a comprehension question. So if I understand correct, I think there are three uses of the word equilibrium. So there is one which is some sort of informal sense which we just observe when we look at a galaxy and we see that the various stars have a mean velocity or something like this, which we just, everybody agrees. Then there are two types maybe of precise mathematical definition of equilibrium, one which is adapted from the case of the particles in the box, which doesn't apply, and the other are strategies to define a new notion which may apply, and which may be some sort of explication of what we mean by equilibrium in the initial just appraisal of what we would like to call equilibrium. Is this what is going on or not at all?
Yes. One of the points that we want to make is that the notion of equilibrium that you would use for gases in a box that are short range doesn't apply here. So you need another definition of equilibrium.
Yeah, but there's also an initial intuition, as you said many times. They are in equilibrium.
Yes,
so there is,
yes.
There must be a sense in which they are.
Yes.
And you need to find a precise mathematical way to define it.
Yes.
Something which is like what is done in statistical mechanics, which is analogous, but which applies here instead.
Yes. That's the starting point. That you observe systems in what you would call equilibrium, and you want to account for that. And then the question is whether you can use the same definition of equilibrium that you use in statistical mechanics, or you need to redefine equilibrium. And our project is to redefine equilibrium.
Okay.
But to both give the same qualitative picture.
That's hard to say. What do you mean by qualitative?
The thing that you're starting off trying to explain.
Yeah, at least both give an account of some constancy of macroscopic parameters in time, right? So we have a system that can be described by some parameters that are constant in a large time scale. In that sense, qualitatively is the same, but then if you look at that from statistical mechanical point of view, then it will not be the same. So the velocities in the end will not correspond to Maxwellian. equilibrium, and you will see some differences if you look at that microscopically, right? But macroscopically, yeah, it's qualitatively the same idea. That's the motivation also for trying to treat these systems as equilibrium and try to give a statistical mechanical account.
But that's what you want to explain, right? The data is the constancy in the parameters and so on. This is what you want to give an explanation for.
And not only an explanation, so this is a little bit more than that. The idea is try to also predict for how long the system will stay in the equilibrium that we observe. But it's not only about explanation, it's also about prediction.
Because you said there is already an explanation for why they have reached that stage, right? It doesn't, but you want to treat it.
You want to do more, exactly. So that's why I'm saying it's not only about explaining, it's about also being able to predict the same, and that's why we think that the analogy is useful. Maybe it's heuristic, but it's useful in the sense that you want to do, hopefully, in this astrophysical system, the same that you do in the magnetization flip case. So you want to be able to determine this lifetime of this metastable state, for how long the system is going to be in one of those states. How long did it take for the system to achieve this state? So, and the idea would be try to do something like that also in this case of long-range interacting systems.
It's much clearer.
You want to ask something? I know it.
I'm not sure. I would like to give other people a chance to make sure they get to ask their questions.
Maybe a stupid question. So, this interesting case where the limits don't commute, right?
Yeah.
Is there a sense in which you could kind of take use of both directions? I mean, is one sense of taking the limit, or the other sense, or will only one sense necessarily be physical?
Yeah, that's an interesting point. It depends on what you want to do.
Exactly.
Right?
Yeah, exactly. Yeah. So, do you have perhaps an example where somehow the system, depending on what operations you do on the system, you either take this limit or that infinite limit first? Because I mean, if I remember correctly, for something like the Ising model or so, there's always like one sense which seems to be privileged from the physical point of view, while the other one we often dismiss or so when studying it. But did you ever come across a case where?
Yeah, I think both are physical, which make it even more interesting. That's why I point that out.
I think that's my question. Whether both,
Yeah. So it depends. Also, consider, and again, here the analogy with the magnetization flips help because it's closer to us than, or to me, than the long-range interacting system. So if you want to give an account of equilibrium in the sense of most likely states, right? Then it makes sense to take the infinite time limit before. Because only by waiting, by considering stationary probability distribution, you will give an account of this average of the most likely states. Right? Now, if what you want is to give an account of the particular state in which the system is in a laboratory, for example, you might want to add a finite time scale to your system. And in that case, it would be more useful to take the thermodynamic limit before the infinite time limit, because you want to obtain a stationary solution on the system in which the state in which you will observe the system.
Right.
So it basically depends on what you want to do, and that's the same thing for the long-range interacting systems here. So if you want to, there are other problems that appear with long-range interacting systems in equilibrium. That's when you're already defining Boltzmannian or Gibbsian equilibrium. There are people working on that And then you have inequivalence of ensembles and all these other oddities that appear when you have equilibrium description of these systems. But you might be interested not in this evolution towards Boltzmannian equilibrium and all these oddities that appear there, but you might be interested in giving an account of the state in which these astrophysical systems actually are.
Yeah.
And if you want to do that, then you cannot take the thermodynamic limit, the infinite time limit before the thermodynamic limit. It's more convenient to take the thermodynamic limit before the infinite time limit.
Yes. Okay.
So again, the analogy here is useful.
Cool. Yeah.
And that's also a nice aspect because precisely there's no correct way of taking the limit. It depends on the question that you are asking.
Yes. Yeah. So, please.
I have one more question.
Yes.
To get clear on that talk of prediction and qualitative comparisons, prediction to me sounds like quantitative. You want to get something quantitative out. Maybe I'm wrong about that, but assuming I'm right, is the idea that the analogy between the long-range interacting systems and the short-range symmetry-breaking systems is of a sort of a qualitative nature. The comparison is, or yes, so that the parallelism is based on qualitative features of the aspects, which are used to then import ideas that have been successfully applied to the other case, to the case of the elliptical galaxies, to model them and presumably then make quantitative predictions. Is that the process?
Absolutely right.
Okay,
That's,
okay, thank you.
I wish I would have said it like that. Yeah, that's exactly what we want to do. So the analogy helps us to give a qualitative understanding of equilibrium that motivates quantitative research. What we cannot do with the analogy is just extrapolate the quantitative results that we have because we are not dealing with the same equations. But it helps us to not only give an explanation of equilibrium, which is something that, as you said, it was already done with Lindenbell and this idea of violent relaxation. It aimed to give a quantitative explanation. But you can use the analogy to understand qualitative equilibrium in a way that motivates the quantitative research afterwards. That's exactly the point that we want to make.
What sort of predictions could these models then lead to? I mean, predictions which are somehow empirically testable.
Mm-hmm.
Because I mean, presumably you could say like, well, now with my model I understand how the relaxation or the final state or the late stage or whatever depends on the initial states. Now I'm observing several newly born collapsed elliptical galaxies with different initial conditions that I can observe, and now I watch and see whether this is going to be. That's not going to work because this will take billions of years, and there's all sorts of ways in which that's not going to be an empirically accessible or testable thing. So, what are the empirically testable sort of predictions, if any at all, of these models?
Yeah, not yet. It's a little bit.
But do you have a goal? Is there something that you think is, at least in principle, something that could be observed from astrophysical data that could maybe be modeled and predicted?
I am just speculating here because I haven't talked about this precisely with Lupo.
Mm-hmm.
But just making predictions and being able to test those predictions would not be realistic because we are talking about a lifetime that is much larger than our life, right? So in the magnetic flip, you can do predictions, right, in the laboratory and consider not a big number of particles, and then you will be able to see this flip. here we are assuming that the flip or the transition to another metastable state will happen, even if we can give a good estimation, that will happen in billions of years. So there is no goal, and I think I can be confident on this, even if I have talked to this. There's no goal of just doing a prediction that you can actually test. So it would be a little bit like trying to make retrodictions in order to make the predictions plausible. But there would be no way, as far as I see it, to test those predictions.
So, right, so that I think you could probably do. You could look at the present state of our technical galaxies and say, given our models, they must have evolved in such and such a way, or they're most likely to have gone through these phases, or being in that kind of metastable state for such and such a period. And then maybe if you understand more about the physics of galaxy formation, including all sorts of unknown physics, but that may play a role there, like dark matter and things like that, you might be able to achieve some sort of consistency with other physics that would allow you to be more confident in these models.
Yes, yes.
But maybe you shouldn't completely give up. Maybe there is, something you said that the velocity distributions is not, or predicted by some people are not completely Maxwellian, but somehow different. But maybe there's something in these sort of distributions, some sort of signature you could find in that, like in a momentary state of a galaxy, more or less, that could reasonably be empirically accessible, that somehow comes out of these models. And,
yeah, but that again will be on the retrodiction kind of strategy, and not the prediction, because one of the goals here is also try to predict for how long the system is going to stay in that state.
Yeah,
that would be a prediction that you cannot test, but of course there is a hope, and that's what they are trying to do, of based on the distributions in which they observed, try to make that compatible with quasi-stationary solutions of the Blasov equation, right? And then try to explain more precisely and more quantitatively how the system evolved to that particular state. That's something that they might want to do. But it's not properly a prediction that can be tested, because the predictions that they want to make are just in a very long time scale.
yes.
I mean, they're logically impeccable, right? So they're just.
What did you say? Okay.
What about numerical simulations?
Yeah, that's one of the strategies. Yeah, but then you have to trust in numerical simulations.
Yeah, on independent grounds.
They are doing that. They are doing that with the Hamiltonian mean field model. They are doing computer simulations as well. But again, so one of the predictions that they want to make are just impossible to test. But the explanation of how systems have evolved to the form that we observe them, that's something that, well, it's not a prediction that you will test, but it's something that an explanation that will be made plausible, right?
Okay. Please join me in thanking Patricia.
Thank you.